Hello, everybody. This is the third lesson for Lesson 7, and we're going to be talking about effect sizes and meta-analysis. Effect sizes is basically the size of the difference between potentially two groups or more, and then we have a meta-analysis, which is really a statistical procedure where you group a bunch of studies together and try to determine what the overall message or theme might be. So the first is the effect size. Now, effect size is a statistical tool used to help evaluate the size of a difference, such as the difference between two means. Now, it's helpful when comparing the results of different studies, being the results would need to be addressed on the same scale. In other words, you need to standardize them. Now, the most straightforward way to express differences in terms of standard deviation units is using the lowercase letter d, and it should be italicized. And you would do this instead of using raw scores. Now here is the formula, which we'll talk about in just a moment. Now here's the formula again, and you have the m lowercase e is the mean from the experimental group minus the m lowercase mc is the mean from the control group, and then again you would divide that result by the standard deviation. Now, there are three standard deviation units on each side of the mean. Thus, the D, standard D, has an effective range of 0 plus or minus 3. Okay, so 0 would mean there'd be no difference between the means, and then minus 3 or 3 would be the maximum difference between the means. Now, a negative value of D indicates the effect is in the opposite direction of what was predicted or the hypothesized change. Now here's a table of two different studies, and what you see here is this is the statistics from study 1, statistics from study 2. And again, here is the group mean and standard deviation, experimental group for the first study and the control group, and the difference between the two would be 5. Now in the second group, you would have the difference between the two groups would be 12. Now looking at this, you would assume that maybe there might be a difference in terms of the effect size of the study 1 versus study 2. However, what would need to be considered is the fact that was the scale used the same between study 1 and study 2. So the same difference between, let's say, 1 unit difference here may not be the same 1 unit difference here, and that might be the difference, or what might be seen as the difference between the two means. Simply the scales were different. However, after doing the analysis, we noticed that the effect size in study 1 was 1.25 versus study 2's, which was 0.85. This would indicate that the effect size difference was greater in study 1 versus study 2, which would indicate that the changes or the effectiveness of the treatment in study 1 appears to be more effective than in study 2, because of the fact that you have a larger effect size in the study 1 versus study 2. So again, simply looking at the difference between the means in study 1 versus study 2, people might conclude, well, there's a big difference between study 2 versus study 1, so this must have had a greater effect. But again, when looking at the actual effect size, the opposite occurred. You notice that there was a bigger effect size here in study 1 versus study 2. That's where the effect size would become handy. So to kind of emphasize, the effect size indicates that there was a bigger difference in the experimental group versus the control group in study 1 versus study 2. So it appears that this treatment was more effective in study 1 than in study 2. Now there's a way to you can calculate effect size using a calculator, and we're going to show a quick video of how to use this calculator in determining effect size.
Have used in the past. I don't use this too much anymore just because SPSS can do a lot of this for me. But this one's a really easy one. So we would take our means from each group. So again, the mean of group 1, And then if you recall, I used the same effect size here, so we'll just do the one for study 1 to get the effect size. The standard deviation was 4 for both of them, so we got the mean of 10 and 5 and use standard deviation of 4 for both. So we just plug those in here. Hit compute, and there you go. We get our Cohen's d, so our effect size estimate. This is a correlation effect size estimate. It's a little bit different, and typically you have to square this. And for interpretation's sake, you would square it to get r squared, so the amount of variance that is explained by which group the person was assigned to. So, but this is the one we're going over now, this Cohen's d, or effect size estimate of 1.25, and that's what we got in our calculation by hand. So you can see it's a little bit definitely more efficient to do it online.
So again, that was a video of how to quickly use a calculator to determine effect sizes. And again, just to emphasize the difference expressed as raw scores versus values of D. Again, if you look at the raw score difference in means, you again conclude that study 2 must have been more effective than study 1. But when you standardize the scores using the means and the standard deviation of each study, you notice that their actual effect size in study 1 much bigger than study 2, indicating again that the study 1 had a more effective outcome in the experimental group than in study 2. Well, now you notice that in the previous example that the standard deviations between the experimental group and the control group were identical. They were 4. But that usually will never happen. So usually you have a difference in the standard deviations between each of the groups. Well, in order to account for this, you have a formula here that takes into account the pooled standard deviation. Well, to calculate the pooled standard deviation, you use this formula here. So for example, using the standard deviation of the experimental group, 4.25, putting that here along with the standard deviation of the control group. Again, you would square each of the values, add them together, divide by 2, and then do a square root, and you would end up getting 4.03. Again, you could calculate that by hand, and then you simply would calculate the effect size by taking the mean of group 1 minus the mean of group 2, and then you would subtract those two, and then the difference would be divided by this pooled standard deviation, and you would get the 1.25 or 1.24. Now, instead of doing it by hand, you could again use the free online effect size calculator, and it automatically uses the pooled standard deviation formula because of the fact that most likely it would be very rare to have exact standard deviations between two groups. So again, this value here was very close to the value we had previously of 1.25. But again, as the differences between the standard deviations are greater, the differences would be much different between what we got before by hand and what we got here by the calculator. So again, usually using the standard deviation, using the calculator can kind of control for this, and probably be a better use of your time as well. But it's good to know how to do it by hand. Now here is the interpretation of effect sizes. Now typically, as you saw in the calculator, it was reported in Cohen's d. And this is often described to values of d using the following classification system. So again, here's the list of what a effect size difference would be. Typically in the type of research in kinesiology, you would get something below 1. If you do get an effect size above 1.4, that might be an indication, at least in social and behavior research, it might be an indication that the data was collected incorrectly or the analysis was done incorrectly, and hopefully this wouldn't be the case, but the data might have been manipulated by the investigator. Other reasons potentially for an extremely large effect size might be the fact that the participants might have done things outside of the protocol that might have enhanced the effect of the protocol or the intervention on them, or the individual or the investigator may have had a biased sample where they recruited individuals that might, from a small sample size, that might have increased the chances of seeing large differences, for example. So these are some of the considerations you should look into or think about when you see, at least in our type of social and behavioral research, the very, very extreme large effect sizes. Again, most would be below 1. Now you can calculate effect sizes in SPSS, which we'll show in a little bit, but these statistical effect sizes in SPSS would be measured using, let's say, the t-test. And you can also use the compare means function in SPSS to obtain the mean, the standard deviation, and an estimate effect size is known as eta and eta squared. Now, eta, again, is the measure of association between a dependent variable, that is interval or ratio data, and an independent variable, that is nominal. So again, taking an experimental group versus an intervention group, or excuse me, an intervention group or experimental group versus a control group. Or you have eta squared, which is the amount of variance in the dependent variable explained by the independent variable. We'll show that in a minute. Now, eta and eta squared can also be attained in all ANOVA applications. So the eta squared, again, is kind of similar to when we had the Pearson moment correlation, and we squared it, and we saw a percentage. Well, again, the same thing as eta squared would be you would have a percentage, and then that would kind of explain the variance that is due to the intervention that you could use. It'd be very effective. All right, so here's the output of an effect size in SPSS, where we're comparing means and we're assuming that it's a post-test only comparison between a control group and a treatment group. And the reason this would be important is that you would need to include, if it was across time, multiple time points, you would need to do some sort of repeated measures of ANOVA that we've talked about previously. So now looking at this table, we see that there appears to be a significant difference between the two groups, looking between the treatment and control. And you can see that you would expect that because there's quite a bit difference in the mean scores. But what would this mean? And well, looking at the measures of association, looking at the minutes per week of physical activity, it appears that the eta is 0.43, the effect size. Now, the percent of variance, squaring this eta, gets a percent of variance, which is close to 19%. So about 19% of the differences between the minutes of physical activity has to do with the group assignment. So let's watch a short video of how this was calculated doing SPSS. Again, you can calculate or do this as well, doing the virtual classroom through ITS and using some of the fake data that I've included in the lesson folder.
This is the same sample data set we've been working with, and I go up to Analyze. I'm going to go to Compare Means, and I'm just going to use the means option. I'm not going to do the independent samples t-test because it does not allow me to get an effect size estimate, nor does the one-way ANOVA, which we'll talk about later. So we go to compare means. My dependent variable in this case, we already said it's minutes per week. My independent variable is group assignment. I don't have to indicate anything with the groups. It automatically does that for me. There's no options that I need to check except for here at the bottom. I do want my ANOVA table and eta. Hit continue, hit OK, and here is the output that I get, and it's the same thing that I just uploaded. And again, this is the amount of variance, so 19% of the variance in moderate to vigorous physical activity is attributed to the effects of what group the person was assigned to. And we can see from the mean difference that effect that the treatment group is the one getting that effect, So, okay, so that's one.
So just a quick note, this is similar tables, but instead of using the ANOVA that we did here, the one-way ANOVA here, or excuse me, the ANOVA comparisons, here we use the GLM, the General Linear Model, and the outcomes are exactly the same between treatment and control that we saw previously, because again, you see the treatment and the control. There is a significant difference as we showed before. The difference is it provides more information regarding the eta squared value. So it allows you, it's a little bit more interpretation. So that's the advantage of using the GLM. And we're going to watch a quick video of how this was obtained.
Yes, or you're tuning out at this point. That's your prerogative. So general linear model, I'm going to go to univariate. And now again, we've got our dependent variable. We need to say that's moderate to vigorous physical activity, our fixed factor. So it shouldn't change. It's either 0 or 1 is group assignment. And then basically the only thing I need to do is go down here to options. And we can get our main effects and all this stuff. Just because that's what we're used to doing. But what I really want to make sure I do is click the estimates of effect size box, hit continue, say OK, and then here we go. And if we skip down, I mean, we can see here's our pairwise comparison, treatment and control. It's saying compared to the control group, the treatment group did 82.564 more minutes on average of physical activity, and that was a significant difference. And then again, here is the partial eta squared, so 19% of the variance was explained by group assignment, and that effect of group assignment was significant at the less than 0.01 level.
So let's talk about what would happen if you wanted to do repeated measures. Looking at, let's say, the weight loss treatment over time, baseline to end point. So you would use the GLM with repeated measures of ANOVA. So that would give you allow you again. That would give you automatically the eta squared information. So using this GLM repeated measures, the first thing you'd want to do is you want to make sure that there is a significant difference between the treatment and control group, in this particular case being BMI. And as we see that there is a significant difference, so then we want to find out how would this study compare to other similar studies. So looking down here at the table, we notice that there's a partial eta squared, which is similar as eta squared. And we notice that, again, changing that decimal to a percent, about 11% of the change in BMI is due to the group that the person has been assigned to. And we can see that that effect is significant based on less than 0.000, so less than 0.05. So let's show a quick video about how you would calculate this using SPSS.
I would just go to analyze, again, general linear model, so GLM, repeated measures. And now recall that I have to tell this what I want my factor name to be. I'll just say it's time, and I took measures at 3 different time points, so my dependent variable was collected at 3 different time points. And now I have to choose to define this. And again, we want to highlight, being BMI at pre-test, post-test, and 12 months is in order in my data set. I just highlight those 3, move them over. My between subjects factors is group assignment, and we move that over into the between subjects factor. And then again, I just go to options. I'm going to get my display means for the different groups, compare the main effects of group assignment, descriptives, estimates of effect size. There's a lot of other stuff here, but you could save that for a stats course, and they'll tell you why you would need to do homogeneity tests or get the observed power, but we don't really need to worry about that in this course. So hit OK, and just go. I'm going to skip down to the things that are important for getting the effect size estimate. And you can see, again, here's the table with the pairwise comparisons, and here's the table with the partial eta squared. So it's really simple to do. It's why I like SPSS. It's fairly intuitive. Once you know, get an idea, well, what analysis should I use for this type of data or for my hypothesis? Well, then it's a matter of making sure your data set is cleaned and looks good and in the appropriate scales, and then you just start doing a lot of dragging or point and clicks here with your data set, and it's real simple to do.
So how do we interpret these? Well, there's some things you need to consider when interpreting effect sizes. The first is you might get, in your study, you might get no effect or an insignificant effect, but that actually might be something that could be important. Let's say you might be replicating a study of a previous study looking at drug treatment, and you find that there is no effect. Well, that could be valuable in terms of interpreting the previous results as well from the previous study, because their study may have uh, not performed the study as effectively as they could have. And so by replicating the study, it does raise some questions as to the effectiveness of the treatment. So don't ignore no effects or insignificant effect size changes. Now, the second is a small effect size might represent an important result. Say, for example, normal effect sizes in a particular area of research is 0.1. You might do a study that the effect size might be 0.2. Well, this might have strong implications in terms of outcomes or for health outcomes. So again, small effect sizes need to be in reference to what has been already previously reported. Now, thirdly, a large effect size might represent an unimportant result. Say, for example, you might have an effect size of 0.8, which is a large effect size, but you'd have to take that in consideration with the amount of time, cost, and effort to get that type of effect size. Is it really realistic for a population to do whatever the intervention might have been required to do to see that effect size? So you'd have to take into consideration, again, more than just the effect size in these interpretations. Now further, there are 3 steps to interpreting the differences between means. First, determine whether the mean differences are statistically significant, as we showed in the table. So that'd be one of the first things you want to know, is there actually a difference between the two groups. Then you want to calculate and consider the effect size using the labels discussed here in this presentation. And finally, consider the implications of practical significance of the results, whether it be no effect, small effect, or large effect, using those considerations as we just talked about in terms of the interpretation and implications and its practical significance. So this concludes the section on the effect size. So make sure you understand this. We're now going to move on to meta-analysis. So again, a meta-analysis, we're going to talk briefly about this because you may come across this in your research literature for your project. So meta-analysis in some cases can be considered original research, but it is something, in theory, you can do it for your thesis or dissertation, but it does require a lot of work, as we'll see in a moment. So it's something that's probably not very common in a thesis or a dissertation, but it is something that you should be aware of as you're going through the review literature that you may come across. So one of the things you want to look at in meta-analysis is using the mean difference. And here's an example of a meta-analysis of replication studies or similar studies that were replicated doing similar things, looking at similar outcomes. So you can see the difference between, here's the experimental group mean, here's the control group mean, and then here's the mean difference. So let's say you wanted to find out what is the overall mean difference for all of these. So the average mean difference. So you would simply add and put the mean difference between the experimental and control group for the study 1 here, and you repeat that for studies 2, 3, and 4. Add that up and then divide by the number of studies, and you would end up getting the average mean difference for the 4 studies looked upon. So again, you can simply calculate this by hand, but this might not be the most effective and easiest to do. So, and also, there might be different units of measures that might have been used between the different groups or the different studies, and so there needs to be some way to standardize this type of average mean difference to get so you can have a better way of interpreting the overall and meta-analysis for a group of studies. So here is using maybe a more effective way of determining the results of a meta-analysis using the effect sizes. And this is, again, could be used when you have a different scales of measurement between studies. So again, here's the table of the study 1 mean difference, or the mean, and the control group. Here's the mean difference, the standard deviation, and then using the formula of the effect size as we've talked about before, here's what the effect size would be. And you would do this for each of the remaining studies. And then you would end up doing the average, which simply would be 0.89. So this would be referring to Cohen's d. And the overall effect of the meta-analysis would be large, but something you need to consider is how realistic or is this practical is this size difference. Now again, this assumes with this study that the sample sizes for all these studies were very similar. There are some statistical measures that you could use if the sample sizes are different, but that's beyond the scope of this course. So here are some important considerations when looking at a meta-analysis. Meta-analysis can be used to synthesize the results of a research conducted by independent researchers as a way to confirm the results of a research on a specific topic. So in other words, instead of looking just at one particular research article or study, you would look at a pool or a group of research articles or studies in a given area. Now, although the statistical analysis is objective or unbiased, great care must be taken in how studies are selected for the meta-analysis. So it'd be very important to consider the inclusionary and exclusionary criteria a priority before the meta-analysis was performed. And they cannot be done haphazardly. It needs to be considered beforehand and given great thought, because what data what studies you include and don't include can have great effects on the outcomes and interpretation of your meta-analysis. Now, it might be necessary to conduct multiple meta-analyses across different groups. So you might have different types of groups that it would not be effective to put them together in one meta-analysis, but rather you would group them into different meta-analysis, and that would give you a better idea as to maybe the effectiveness of a treatment, as opposed to pulling them all together under one. That might end up not giving you the true outcome or the effect size that could be washed out because of the different types of groups that have been being used. Now, something to consider when you're doing your meta-analysis is called publication bias. And this may lead to only studies with significant results being available for the meta-analysis. So journals usually like to only produce or publish where they have significant results, and therefore only the studies that are available to the literature, and the literature is those that have shown differences. And usually, on the contrary, some studies may not be published simply because there were no significant difference. So you have some publication bias and consideration that to take into account. All right, so this concludes this part of the lesson. So make sure that you review this information prior to taking the exam, and also it'll be helpful when doing your project.